In the next, we will discuss the training of a neural network. To be specific, we will consider how to adjust those model parameters so that by influencing the computational steps in the model, and therefore it will modify the final output of the model so that the output changes to the direction which is desired. In the following discussion, we'll concentrate on how to calculate the adjustment of those weights. That means the W matrices. The methodology we will discuss is straightforwardly extended to the computation of adjustment of the bias. So let us first consider perhaps the simplest possible construction of a neural network. We have a layer of perceptrons. Remember that it means a family of a group of linear models, and we make a group of two. That is simple, and then have an output, and then we want to consider what does training the parameters in such a network mean. We will, it turns out that the learning process or the training is actually conceptually a method of reversed computation, because as a start we will be able to, which is most obvious to us, is where or what is the objective, and that is to reduce the loss. And if you know the output of the network, and then you compare that to the desired output, it is straightforward to compute how to change the output of the network so that the loss is reduced. And then from there, we will gradually compute how to change the model parameters that is controllable to us so that the output of the network changes to the desired value, and so that to change the loss. So the computational steps is reversed, and therefore there is a name of backward propagation. To be specific or mathematically, what we want to do is to compute a gradient of the loss function with respect to the model parameters. So let us write out the computational steps carefully, so make the following discussion more clear. Say, for example, the network is going to predict the class of a sample, and the desired class of this sample, the norm class, because this sample is belonging to the training dataset, so we know the desired output is a positive class, and the network will output a probability. I say that is a y. I know the denotation is slightly different because I would like to use a lot of different letters in this discussion to make the computation more clear. So the output of the network is y, and the desired output is a positive class. Well, we can interpret the y as the probability of the sample belongs to positive class. If this is the probability, we would like it to increase to 1. Okay. And please recall, our network has a structure like this. Input, and with one layer of computation, has the same number of 2 outputs, and then have another layer of computation. We have some value here, and with conversion, and then you get a y. See, the conversion is what we have discussed, sigmoid conversion. And let us call this value to be b. Then let me show the network structure here. So let this value to be b, and the sigmoid conversion goes like this way. And here is 0. Mathematically, the equation should be 1 over 1 plus epsilon to the power of negative b. So you can see that when take a very specific example, say if b for this particular x0 and x1 for the particular w parameter, and everything set up, just for the sake of discussion, let's say b is 0 now. And if you substitute 0 into this equation, it's easily get just half of the probability. Obviously, you want b to change this way, so that the y, the probability, will move up this way. It is easily to find that when you have a delta b, the y will not move up as much as you move right in the direction of b, for b. So you have the derivative here. The derivative, if you take the derivative using this equation, you get derivative of this with respect to b when b is b is 0, and this is equivalent to c, y is 0.5. This derivative is equal to 0.5 as well. That means if you change delta b by 1 unit, you will change y by 1 unit as well. By change y of 0.5 unit. Well, now we have arrived at this point. We know that if we change b by 1 unit, the final output will change in the same direction of half of the unit. And because we know we want to push up the final output so that it is it goes towards positive 1, then we have the idea of how to change b. And the key question now is how to get in this information back to the remaining part of the network, and so we can know how to change other parameters. So to summarize what we arrived so far is we want to let the output probability y to move up, and we know that if we move b by 1 unit, y will move up by 0.5 unit. And the question is to consider this calculation procedure and therefore to calculate how to change those w and those u so that we can change b, and so that correspondingly we can change y. Okay, the next logical step is to consider how the parameters of the second layer, this layer, because b is the value here, we will consider how the parameters of this layer of neuron to affect the value of B, which moves us to this part. So, well, in this slide, I have shown how the B affect Y, and in this part, we will investigate what determines the value of B. To write it down explicitly, let us call the output of the first layer computation here are H0 and H1. And the B value is a very simple sum using the H and the parameters in the second layer. They are H0 times U0 and H1 times U1. Note in the denotation on the slide, I have also put a 0 here. That is to represent, it's corresponding to the unique output of the second layer, because there is only one output of the second layer, so I remove this. So this computation gives us B. There are two parts of this computation as shown in the slide. That is H vector in this direction and U vector in this direction. This inner product of H and U gives us B. So we can consider how to change U and how to change H to arrive B. Because H is the input of this layer, we will discuss this later. We adopt the reversed direction of computation. We can first consider how to change U so that how the U change in U affects the change in B. Well, let's consider one element of U. Let's see this element. It is not difficult to imagine that if you change U1 by 0.01, then let me move this a bit, maybe to this part. Then B will change 0.01 by H1. And this part of the computation doesn't contribute how U1 affects the value of B. And therefore, we can write let me move this up. It's a bit crowd here. Okay, and therefore we can write the change of B is the change of U1 times H1. And please remember the change of Y is a change of B times 0.5. So if you go this way, we will have the change of Y is the change of U1 times H1. Therefore, it affects, let me move this. the change of y is change of u1 times h1, therefore it affects b, and this is times 0.5. And correspondingly, we will have we will see the u1 will affect y by h1 times 0.5. We'd rather not explicitly write 0.5 here. Instead, we will see it is h1 times how b affect the final value y. Similarly, we'd like to see, let me remove this, using the exactly same kind of derivation, we can see how u0 affects y is just h0 times how b affects y. If we go to this illustration, it is not difficult to understand. That is because both u1 and u0, I probably don't have the good. Oh well, I have the correct superscript, but I have written as a subscript in the handwritten derivation. You get the point anyway. This pair of parameters contributes to the final output of the neural network through b, and they contribute to the value of b by being multiplied to this pair of parameters, and therefore we write it as note, this is now a loaded notion. This is not an element, it is a vector. This vector, the h vector times this. Please also note that we haven't specified whether this vector is a horizontal one or a vertical one, because there are two vectors. Later we will consider matrix, then they will consider the direction of the matrix. And also, we can, using exactly same kind of derivation, get correspondingly how h affects the value y. Because h and u contributes in a very symmetric way in the computation of the value of b. So here is the illustration. Actually, the illustration is exactly the same. So h and u, they combine with each other to b. And the key here is when you calculate the contribute of one part, you keep the other fixed. Here is maybe another way of illustrating the computational process, but using slightly different symbols. Say we have x1, x2 times w1 and w2. There is a times, there is a multiplication operation, and then you have the result of the multiplication, and then we add up the result of the multiplication and get the final value. And when you want to calculate how the final value is affected by the elements, you backpropagate the the influence and from the result to the operands of the calculation of the computation. Okay, this is for this part of the initial part of the backpropagation algorithm. In the next, we will consider how to organize the computation in the format of matrix multiplication, similar to our derivation of the forward computation.